Okay, ma'am, start பண்ணலாம்.
Nilofer, you can start.
Okay, ma'am. Good morning, everybody. I am Ansha Nilofer, the head of the physics department, Anne Hajra Women's College, Malapalayam. It's my immense pleasure to welcome you all for this auspicious occasion. Let me first thank our Almighty Allah, who is most merciful and most beneficent, and who guides ourselves to arrange such a wonderful sessions. And I would like to thank our management people, that's our President, Engineer S.K. Sayyid Ahmad sir, and Secretary, Engineer S.K. Guda Muhammad sir, for their valuable support for arranging this wonderful webinar. I would like to extend my warm welcome to our respected principal, Dr. K. Rajab Fatima, who gave a constant encouragement for organizing this grateful webinar, namely E-Series Lecture 2, arranged by Anne Hajra Women's College, Malapalayam, in collaboration with EduX, the learning people, in which we are going to enrich our knowledge in the topic of emerging solar cell materials and characterization. And on behalf of our management, I welcome the honorable invited speakers, Dr. X. Sahaya Arjun, Director, Academics and Research, PSN College of Engineering and Technology, and Dr. E.M. Moti, Associate Professor, Center for Scientific and Applied Research, PSN College of Engineering and Technology, Tirunelveli. Welcome you, both of you, sir. And I extend my warm welcome to all the panelists and organizing committee members and faculty members and research scholars from various institutions. I welcome you all the participants and I welcome everybody once again. Now, I would like to invite our respected principal to deliver her presidential speech. Over to you, ma'am. Thank you.
In the name of Allah, the most gracious and most merciful. As we all know, education is the art of cultivating hopeful environment and relationship for learning. It's often said that we are learning all the time and it happens every time. Learning is both a process and an outcome. Thus, it has paved way for these types of webinar in times of pandemic also. So in this regard, I am proud and glad that we have eminent personalities like Dr. X. Sahaya Arjun, Director, Academics and Research from PSN College of Engineering and Technology, and Dr. E.M. Moti, Associate Professor, Center for Scientific and Applied Research, PSN College of Engineering and Technology. We are really grateful to you, sir, for having accepted our invitation to provide an e-series of your lectures on these webinars to our college in association with our college. I would also like to pay my indebtedness to the management for their wholehearted support which they give for the betterment of the students, staff, and for the college. And I also congratulate the HOD of the Department of Physics, Mrs. Nilofer, and the organizing committee members, Dr. Sri Devi and Dr. Lavanya, and others for their support in organizing this webinar. And also my appreciation to my computer science department staff, Mrs. Booma and Mrs. Mumtaz Begum, for the technical support extended to me in organizing these webinars. Thank you. And I once again welcome all those who are on screen and for all the participants who are here. Thank you very much. Over to Sri Devi. Sri Devi, you can carry on.
Ma'am, Sridevi ma'am is not here. I think she has some internet connection fault.
Yes, ma, she is in.
Yeah, now she is joining.
Yeah. Over to Sri Devi.
Sridevi ma'am, unmute yourself.
Okay, ma'am.
Start.
Good morning to all present here. I'm happy to introduce today's first speaker, Dr. Suresh Arjun. He was graduated in physics from Madurai Kamaraj University and got his post-graduation from Bharatdasan University, Tiruchirappalli. He was awarded PhD in physics by Manonmaniam Sundaranar University. His area of research includes crystal growth, nanostructure, and composite materials for energy applications. He has handled many research projects funded by national funding agencies to a tune of rupees 2.5 crores. To his credit, he has published more than 70 research papers in refereed international journals of high impact. So far, 12 scholars have successfully completed their PhD degrees under his guidance. He has organized 14 national and international conferences, student internship programs, workshops. He is a life member of Material Research Society of India, Photonics Society of India, Indian Association for Crystal Growth, and Indian Society for Technical Education. Currently, he is serving as a Director, Academics and Research at Pearson College of Engineering and Technology. We're happy to have you, sir. I request you to take over the session. Over to Shajan, sir. Thank you.
Okay, thank you. Thank you for your nice introduction. So, can I start my presentation now?
Yes, sir.
Yes, sir.
Hope you can see my slides.
Yes, sir.
Yes. So today my topic is on metal organic framework aerogel composites, an emerging family of hybrid nanomaterials for energy applications. And Ramazubu and Albin are my students, PhD students who have successfully completed. And this is our campus. So my presentation will cover all these 5 topics that I will be briefing about the renewable energy sources. Then I will be talking about the solar energy and solar cells. Then porous materials. Then about metal organic framework and aerogel composites, usually called as MOFACs. Then I will be discussing our experiments with MOFAC as the photoanode. So if you see the MNRE report published in December 2019, the cumulative installed power capacity in India is given here. And if you see from this region, from hydro to solar, we call as the renewable energy source, energy generated from renewable energy source. And of course, these are all non-renewable. And the projection for 2029-30 is also given here. If you see, there is a huge increase in the production of solar energy in the next 10 years. Almost it is a 4-fold increase in the energy production. And that's why everywhere the solar energy is now coming very, very important. But this is not an Indian scenario. If you see the entire world scenario also, you can see by 2035, the solar energy will find to have a increase in the production of solar energy. There is a very steep increase, huge increase in the production of solar energy. And you can see by other renewable energy sources, solar and wind are going very high. And that's why the discussion on solar energy becomes very, very important. And why we need this solar energy and what is its importance that we have to see. So first of all, solar energy is available free of cost It is a renewable energy source. And you know, it's an eco-friendly, has no environmental hazards. And the most important is the energy received from sun is enormous. A huge amount of energy is being received every day from the sun. If you calculate the energy received, the total energy that is coming out of the sun is 179 petawatts. And you know, 1 petawatt is 10 power 15 watts. And approximately 29% of the energy coming from the sun is being reflected by the atmosphere, and nearly 21% is being absorbed by the atmosphere. So we will be losing around 50% of the total solar energy that is coming from the sun, and the remaining energy is being absorbed here. Of the remaining energy absorbed here, you know, the earth is made up of 2/3 of water in the earth and 1/3 of land is available. Therefore, we will be finally getting around 30 to 35 petawatt of energy from sun. When you compare this amount of energy with the energy that is being used by the entire world, which is of the order of terawatts, it is 10 power 12 watts, whereas this is a petawatt, still it is very, very high. But how we are going to harvest this 30 to 35 petawatt of energy that is useful for our applications? That is very, very important. Whether we are able to harvest all the 30 to 35 petawatt of energy. That is the task in the solar energy harvesting. This, all physics you know, this is a black body radiation spectrum. And you know, Planck's law says that as wavelength increases, there is a shift in the peak of the maximum spectral, the wavelength. And that wavelength gets shifted towards the lower wavelength as we increase the temperature. So 4000, it is here. For 6000, goes below 500 nanometers. And the temperature of the sun is around 6000 Kelvin. So this peak corresponds to the black body radiation of the sun, because we know sun is considered as a black body which is continuously emitting radiation. And if you compare this spectrum of the sun, which we call the black body radiation at the temperature of the sun, we find that the entire visible region is covered under the spectrum. That is the importance of the solar energy. Of course, it has the UV radiation and also a significant amount of IR radiation, that is the heat radiations. So that is there. But if you see, the entire visible region is covered by the sun's radiation. So we are able to harvest the complete solar energy which is in the visible region. So this is the second important reason why solar energy is preferred. The device which converts light energy into electrical energy, that is solar energy into electrical energy, is what you call a solar cell. And solar cell functions in the form, in the principle of photovoltaic effect, which is creation of voltage and electric current in a material, not all materials, the specific materials upon exposure to light. And it is a combination of both physical and chemical properties. And photovoltaic effect was discovered in the year 1839 by Edmund Becquerel. He is the father of Henry Becquerel, who later discovered radioactivity. So he discovered this effect in 1839. Now solar cells. Let us see as simple how it works and what is the main events that should occur in order to a solar cell to convert light energy into electrical energy. Three processes are very, very important. One is absorption of light and consequently generation of charge carriers. So absorption and generation. Then the generated charge carriers has to be separated. That is the second process, what you call the separation of charge carriers. And the separated charge carriers should be collected at the electrodes so that an electric current is coming. Therefore, the third process is collection. So absorption, generation, that is together, and separation and collection. These three processes are common for a photovoltaic effect to happen. And this is common for all solar cells, whatever it is, whether it is a silicon solar cell or a dye-sensitized solar cells or an organic solar cells. These three processes has to happen. So this is where this is a common solar cell that you might have seen everywhere. It is being installed, and it is a silicon solar cell made up of silica. And this is being a commercially available solar cells which are installed in almost all areas throughout the world. And why silicon? Why silicon is preferred? But silicon is the second most abundant element on Earth. So it can be easily obtained. And the production of high quality crystalline silicon is a well-established process. The technology is well established. So how much, whatever be the quantity we require, we can easily produce a high quality crystalline silicon. And the third important property is it has good electronic semiconductor properties, which are favorable for photovoltaic conversion. So its band gap is around 1.12 electron volt at room temperature, and it absorbs the entire visible spectrum. So these are the very, very important properties of silicon, why silicon has found such a huge application in solar cells. And silica is nothing but sand. So that you know, everywhere we can find sand. That is why I said it's the second most abundant material in the earth. And silica is obtained in the form of SiO2, which we call as silicon dioxide. And when we add carbon to it by a process, it is a chemical process, which is a well-established process. Of course, it involves high temperature and everything. And we can convert the silica, that is a sand, into silicon. But silica as such, it is not a good conductor because you know it is a semiconducting material. So the motion of electrons in a semiconductor will be in a random way. Therefore, we cannot use that silicon as such. Therefore, what we do as physics students, you know, we make N-type semiconductor as well as P-type semiconductor by adding a trivalent impurity or a pentavalent impurity. So that accordingly we get, this is a pentavalent, therefore this is a trivalent, boron and lead. And we are getting an N-type semiconductor and P-type semiconductor. And subsequently, we are making a P-N junction. And you know, I don't want to go into the detail because these are our fundamentals. And in a P-N junction, we will be getting a depletion region across the junction. And a voltage barrier is formed. And we say this is the barrier potential. And this is the normal conditions. This is the normal conditions. Now, in such a P-type and N-type combined, a P-N junction, a depletion layer is here. Now, if sunlight strikes the depletion region, now charge carriers are being generated in the depletion region. And already there is a potential on either sides. One side is positive and another side is negative. Therefore, the holes are attracted towards the negative side and the electrons are attracted towards the positive side. And hence, a charge gradient is formed. Or what you call excess of charges are available in the N side and the P side. And due to this, a potential difference is being created across the solar cells. Now, if I connect a load outside, these electrons will move in the external circuit and recombine with the holes in the P side. And this is a continuous process as long as the sunlight is available. And this is how our silicon solar cell works. So everything is fine, then why we want to go for other type of solar cells? That is a question. So if you see, for everything there is a limit. And similarly for silicon photovoltaics or silicon solar cells, there is a limit. And what is the limit? That is the maximum efficiency that can be obtained. That is a theoretical value is around 29.4%, around 30%, 29.4%. It is the maximum efficiency. Beyond that, we cannot increase the efficiency of a silicon solar cells. And what now we are getting, we have recorded up to 23.6. We have come up to this level, 23.6% as being already available. And of course, we are losing 73.7% as in the form of recombination and other effects that we will be discussing later. So we have already reached to a maximum that is around, we are nearing. Now the available efficiency in silicon solar cells is around 27%, which is very close to this 29.4%. And that is the reason why we are going for other materials, whether we can improve the efficiency beyond this 29.4. That is one reason. Second reason, there are also several materials which are even able to give more efficiency than silicon solar cells. But the problem here is silicon solar cell technology is well established because it is there for almost 60 years. They are working on the silicon solar cells. And so about the technology of separating silicon from silica, as well as purifying silicon, is all well established. Several industries are there in the entire world, but it's not like that for other materials, where such technology, such purification processes is not so much available. So these are the different types of solar cells which are other than silicon solar cells, which is being widely studied all over the world. And of course, dye-sensitized solar cells is one of the oldest because it was first reported in 1991 by Gradzel and others, which is being here for research for the past 30 years. And still it is going on. So now today my talk will be around this dye-sensitized solar cells, that our experiments, what we are conducted, and the materials, what we have identified. I will be talking on one side and Dr. Moti will be doing on the other side. Now let us see how the dye-sensitized solar cell works. So it has one substrate, that is a glass substrate, or what you call the fluorinated tin oxide. It is a conducting tin oxides. Normally we call the TCOs, that is light can be transmitted. It's just like a glass slide in which fluorinated tin will be coated. And we call that as an anode. And above this, we coat the titanium dioxide. And above that, we coat the dye. And the titanium oxide and the FTO together, we call that as a photoanode because it is related with the light. That is why it is called a photoanode. And above that, a dye is coated. Then an electrolyte is being placed above that, which contains the redox. It's a reduction oxidation couple that we call as a redox. So it is a redox couple, iodine iodide couple. Then we have another FTO in which platinum is coated. That is platinum, you know, it's a very good conductor of electricity. And that we call as a cathode. So this is the structure of a dye-sensitized solar cells. And this is connected to the external load. Load may be an electric bulb or anything. You can connect to an external source. Now, when sunlight falls on the dye gets sensitized. Therefore, you know, it goes to the excited stage. So this excited electron is injected into the conduction band of the titanium dioxide. And this injected electron is now diffused into the external circuit. And this electron goes round the entire circuit and comes back to the first position. By the time this redox couple would have generated an electron and that is being transferred, this is for electron transfer. So all these process in the entire process is happening, and we are able to make the light to ignite. So talking is very simple because we can say that this is exciting, this is giving the electron to the conduction band, and this electron goes around and we are getting electricity. Everything is over. Everything we can talk. It's very simple. But when we come to the process, practical process, it is a very, very difficult process because you know there is a photo excitation taking place. Here a photo excitation, then an injection of the electron to the conduction band, then diffusion of this one is happening. Then at the same time, a recombination may happen. At the same time, the dye has to be regenerated by the coupled redox electrolyte. Through the electrolyte, it is there. And also you see the titanium dioxide is over the FTO. And immediately above that, the dye is there. Immediately above the electrolyte is there. So everything are interconnected. So instead of electron diffusing into here, the electron may come back to the dye itself. So several photophysical events that are happening. inside the dye-sensitized solar cells. So if you see, these are the various photophysical events. We call that as a very ultra fast as well as ultra fast. Why it's so? It is a combination of several processes, and if you see the time, one is happening in a millisecond and another is happening in a femtosecond. Millisecond, you know, it is 10 power minus 3, whereas femtosecond is 10 power minus 15. And another one is happening in a microsecond, another one is happening in a picosecond. So you see all these are happening between 10 power minus 3 to 10 power minus 15. 10 power minus 15, it is a very, very fast, and that is why we call it as an ultra fast. And this is, of course, a fast process. Of course, for an electron, this is a dead slow process, what you call a millisecond. For us, this is a very, 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 very fast. For an electron, this is the slowest process, what is happening. Even a microsecond process and millisecond process is simply a process for the electron. So this is the combination, and you can see, now you see here, this is the process one, this electron is being excited. And this is being injected into the conduction band, and that is being diffusing into the anode. This is the straight process what we are discussing. But at the same time, it may come back to this original position. That is what you called the excited electron coming to its ground state, and it will recombine with the ground state. This is one possibility. Or the excited electron from the dye is not acquired sufficient energy to reach the conduction band that it can come back to its original ground state. And another degeneration is happening here. That is the degeneration. So all these process, that is photoexcitation is happening, so everything is happening at the same moment. Photoexcitation, electron injection, electron diffusion, dye regeneration, and electron recombination. All these things, almost 7 photophysical events are happening in a dye-sensitized solar cells. That is the major problem in controlling the electron movement, or to trap the electron for conduction so that we get electricity out of these dye-sensitized solar cells. That is the point where so many scientists are working on different type of materials to stop the recombination rate, to improve the electron injection rate and diffusion rate. That way we are working. So dyes, another thing is that dyes, what is the advantage of dyes is it is sensitized both by natural as well as artificial light sources. So artificial light sources means a dye-sensitized solar cells can be kept below a fluorescent lamp. That is a tube light, what is available in our room. You can keep the dye-sensitized solar cells below that and it will be sensitized. But it is not so in the case of a silicon solar cell. So that is a major advantage, because then it is very clear that it can be applied for indoor applications. So you can have this type of solar cells are now being available. That is, there is a company in Japan which is producing for so many solar cells, very just like in the size of your tablet, your tablet that is you are using. So you can put it in your table and you connect your light source and it will be burning. Such type of applications there are there, but still a lot of work is going. Also, a dye-sensitized solar cells essentially has these 4 parts: a photoanode, a dye, an electrolyte, and a counter electrode, which I have explained already earlier. And I will be talking on these photoanode materials, and my fellow colleague, my friend Dr. Modi, will be speaking on the dyes and all these other characterization methods. So porous materials, that you might have heard about these porous materials, and that are broadly classified into, there are several classifications that is being reported in literature, but for our sake, we are taking this classification as microporous materials, mesoporous materials, and macroporous materials. So microporous materials in which the pore diameter should be less than 2 nanometers. In the case of a mesoporous material, the pore diameter should be around 2 to 50 nanometers. And in a macroporous material, the diameter should be greater than 50 nanometers. This is a general classification. So for example, if you take a microporous material, we can say metal organic frameworks, which we are going to discuss today, or Aerogels, that is another type of material. So these are classic examples for microporous. And for mesoporous, we are having MCM, that is a mobile company, MOBIL. You have heard about it, Mobile Composite Materials. They have created one specific type of porous material, which is having a diameter around 10 nanometers. And that is called MCM41. And another one is Aerogels, which we'll be discussing today. And macroporous material, the common example is the sponge. And there is another class of materials, what we called as multimodal porous material. The name itself, multimodal, because it has more than one modes of porous. And we can see about that. So materials that contain multimodal interconnected pores. So it will be having the combination of a micro or a macro, or a meso or a macro, or a micro or a meso, like that. It is a combination. And we say that is a composite materials because it is a combination of two materials with multiple phases. And of course, it should be a continuous phase. And is a non-gaseous phase. Of course, it is a solid. And according to IPAC, you can say this nanocomposite to be a material in which either one of the phases should be in nanometers. Here the two are in nanometers, therefore it is a nanocomposite material. That's a multimodal. And multimodal, as I told you, it is having two types. It is bimodal as well as multimodal. If two things are combined, then we say it is a bimodal actually. Micro, or macro, meso, or micro, meso, macro. Or if it is a multimodal, if all the threes are combined together. So that material will contain its pores of all the three categories. As we discussed earlier, it is containing some pores will be of having diameter around 2 nanometers, and some will be having around say 10 to 20 nanometers, and something will be having more than 50 nanometers. All the three will be present, and it will be in a continuous phase. And it is also referred in the literature as a hierarchical multimodal materials, the combining of two materials having two different porous structures. This is what we are going to discuss today. And multimodal porous materials are not new ones. So they are available in the nature, and they perform multiple functions with the enhanced properties. And one the very important material that is available is your bone. The bone available in your body is a multimodal porous material, which contains different type of porous materials in it. And one, you say this cortical hard bone that is on the surface of your bone is a microporous, and this is a mesoporous. That is trabecular bone is a combination of mesoporous and macroporous. And this is very compact. That is why when it is hit by anything, you will get a fracture. It is highly brittle, whereas this is not brittle. This has more strength than the cortical bone. So a fracture happens on the cortical bone. And not only the bones, and here we can see a lot of naturally available materials that are available in the nature, which are made up of these bimodal or multimodal materials. And coming to our materials, our work, we have two classes of nanostructured porous material, that is aerogels and metal organic frameworks. And this is what we are mixing, these aerogels and metal organic frameworks. A lot of work has been done on metal organic frameworks by most of the chemistry labs in the world. And of course, aerogels also, they have done a lot of work. But combining these two is somewhat a new one for energy applications. So aerogels are first reported in the year 1932 by Kistler, where we have to replace the liquid in the gel without collapsing its porous structure. The reason is, suppose you are having, a volume, you take a cube, which is hollow in the center. Now you have to remove the entire liquid without reducing the volume of the cube. That is very, very important. Normally, we can crush it and we can remove it, or we can heat the material and we can remove the liquid present in. But in all these cases, the structure will be collapsed and the volume will be decreased. But in the aerogel, it should not be decreased. The solvent has to be taken out. We can see in detail. And metal organic frameworks is another type of the porous polymers, and that is being reported long back in 1965. But the work of Omaragi and his co-workers in 1999 put MOF into the limelight. And after that, a lot of work has been carried out, mainly on catalysis. A lot of chemistry process are working on this catalysis. A lot of work is there. Now it is not a new one, but a lot of work is going on this metal organic frameworks all over the world. And why these two materials, both MOFs and aerogels, I have said it's a porous classification of porous materials and as well as nanostructure. And therefore, they have high surface area. If you say aerogels will have the surface area around 300 meters squared per gram. If you take 1 gram of the material, their surface area will be around 300 meters squared. Whereas in MOF, it is still high. It will be coming around 800 to 1000 meters squared. High porous volumes. And then it has high porosities, low density, it is very lightweight, and the very important one is the pore tunability. The pore tunability means if I want to have 10 nanometer pores, I can tune it accordingly. Suppose I want to improve the pore size or I want to decrease the pore diameter, I can do it. That is why according to your application, you can modify the synthetical procedures or you can do some modifications on the material, and you can tune the pores that will be suitable for your applications. These are the advantages what we have in MOFs and aerogels. So incorporating a micro and a mesoporous micro, that micro is a MOF and a mesoporous is an aerogel. So when we combine these two, we get a new material, and that is what you call as MOF aerogel composites, as abbreviated as MOFAX, MOF ACL, AC. And that is being widely being experimented all over the world. And you can see there are a lot of work has been come up in this area, but very little work on energy applications. As I said, these MOFs are being tried extensively on catalysis and absorption studies, not absorption, it's absorption studies. And a lot of work has been carried out in this area. And of course, very few work in this area has been carried out in this one. So now let us see what is an aerogel. Aerogels are nothing but, in other words, it is called aerogels because in the gel you remove the liquid, and in the place of the liquid you are keeping the air. So this is a 3D interconnected network structure possessing high surface area, high optical transparency. All light can pass through because most of the areas are empty, and it has a very low density, very low density. So I have already told you, and this is why in this way you can create a gel. So gel will contain the solid network as well as the liquid in it. Now I want to remove the liquid out of it without disturbing the volume. So same volume you are getting here. If you destroy the volume, then it is called a zero gel. That is a different case. So from a solid, you remove the liquid and retain the structure of the solid as such. And then we call this as an aerogel. And if it is filled with water, we call it as an hydrogel, or with an alcohol, we call it as an alcogel. And if it is filled with an air, that is nothing is present, no solvent or liquid, anything is present, then we call it as an aerogel. And if you see the physical properties of these aerogels, it is, as I said, it is a very low density, very low density. And skeletal density is also very low. And we see the porosity, it is almost 80 to 99%, it is completely porous, so that it can absorb anything. And the average pore diameter, you can have 20 to 150, and the surface area, you can tune the surface area as well as the pore diameter, and it is ranging. All these are reported in the literatures, and its thermal conductivity is very low. That is why it can be used as an insulating material. So the common method of preparing aerogel is by a Solgel method. It is a common method that is most of the researchers will know what is a Solgel. You have to prepare a sol and then you have to make we allow for aging, make to condense and convert that into a gel. The sol is being converted into a gel by taking some days. And most of the people are working on this Solgel. It's a well-established procedure. Now, the main important thing is how to remove the liquid that is present inside the pore. That is a major problem. Major problem in the sense we should not destroy the structure. We have to retain the structure. At the same time, we have to take the liquid or the solvent that is present here. And you know, this is the formula that is relating the capillary pressure and the pore diameter. And you know, if the pore diameter is less, the pressure will be more. And if the pore diameter is large, the pressure will be less. So we have to see that if you increase the pressure, this will break. The walls of the material will break and it is completely collapsing. It should not happen. Therefore, we have to retain. We should be very careful while removing this. So here, you know, this gamma is the surface tension that is there between the liquid and the surface. And of course, cos theta is the interfacial angle. And all these, you know, you as physics students, you know all these things. So the only factor which I can use here is the interfacial surface tension. So if I can reduce the interfacial surface tension, then automatically I am reducing the capillary pressure. So in that case, you have to retain the pore diameter. You should not disturb this. So only one thing is you have to play with this one, this interfacial surface tension, and automatically pore diameter will reduce. Sorry, pore capillary pressure will reduce. Now, how we are doing? That is very important thing that we have to do. There are three drying technique methods are available. One is called supercritical drying, another one you call freeze drying, and another one you call as a subcritical drying. In a supercritical drying, you take that wet gel, put into an autoclave, and you increase the temperature and pressure to its critical point. That is critical temperature and critical pressure, usually normally very high. So if you take this pressure, this is the temperature pressure graph, and if you take this to this point, that is a critical point, it's a point at which the liquid is converted into a fluid. You know, a liquid, a fluid will have no surface tension. Surface tension is equal to 0. So it can easily flow out. So all the liquid or the solvent that is present inside the pores of the gel will be taken away. This is a very good method. And of course, we can say it's a perfect method to prepare aerogels. But the major problem is, so we are increasing, or we are playing at the critical temperature and critical pressure, which is normally very high. So the autoclave in which the autoclave should be closed properly. There should not be any leak, and the autoclave should be capable of handling such a very high temperature and pressure. In other case, this will burst. And that type of accidents have happened in many places in the world, but still that is the one of the best method to prepare the aerogel or to remove the solvent that is present inside the pores. The second method is the freeze drying method. Here just opposite, that you have to lower the temperature. Excuse me. We have to lower the temperature below the freezing point, and also simultaneously you have to keep the pressure below the sublimation. That is, both are important. So this is also an industrial process like previous one, that is supercritical method. Freezing drying is also done in many industries for production of bulk amount of aerogels. So you have reduced this one, reduce the freezing point, reduce the temperature below the freezing point and pressure below the sublimation pressure. Since it is being done at a very low temperature, this type of gels are usually referred to as cryogels also. But here there is one, you should be very careful, as there the temperature is a major, is a, what you take a precaution on working on high temperatures. In the freezing, you have to take precaution. That is, since you are going below the freezing point, sometimes crystal growth may occur inside the pores. Because suppose you say if the solvent is water, then you are going below, you are coming to the 0 point, then freezing takes place. And if the crystal growth is being produced, or crystal growth is initiated inside the pores, now what happens is, when water is converted into ice, its volume increases or density decreases, especially volume decreases, and expansion is happening in freezing. And what happens is your mesopores now becomes macropores, because due to the expansion of water while freezing, this becomes a macropore. So you are expecting a mesopore, but you will be ending with a macropore. So that you have to take care of. And also there we can combine the solvent exchange also here. And supercritical method and freezing drying method or industrial process where we can produce bulk. And the third method is a subcritical drying method, which is a simple method, but maybe it is a somewhat time-consuming method too. And we cannot produce in bulk production of aerogels, but is a lab scale method. Lab scale, we can use it. It's a laboratory process. It's a very good method. Here what we do is, we take the gel and we take another solvent. Say for example, if I am using water as a solvent, the surface tension of water is around 0.7. So I want to choose now another solvent which is having surface tension less than 0.7. Normally, most of the organic solvents will have their surface tension less than 0.7, around 0.3, 0.2, even 0.1 hexane will have around 0.1, and isopropyl alcohol will have around 0.2. So such type of solvents you can choose. So what you do, you prepare the gel, you put it inside the beaker or something, some vessel containing the N-hexane or isopropyl alcohol. You exchange the solvent. This is very similar to the method what we use in your house to wash your clothes. If you want to remove the dirt that is on the clothes, what you do, you apply soap. And what soap does, the soap reduces the surface tension and automatically the dirt is removed. In a similar way, you are reducing the surface tension of the water or any solvent you can take. The thing is, the surface tension of the solvent that is you are using, the liquid that you are using to extract the solvent should have the surface tension less than the solvent. That is the case. That you have to decide. So if you are continuously doing like that, all the liquid which is having higher surface tension will be slowly removed out of the pores. The thing is, this cannot be done in a single stage. You have to repeat and repeat for several times. And finally, that by trial and error method, you can find how many times. In our case, we did for 6 times. So sometimes if you have to go up to 10 times, you have to do this process and totally you can remove the pores. But one problem here, some residues may be present because you may remove the solvent, but the liquid that you are using to remove the solvent, that residue sometimes may be present there. It may be certain cases it's beneficial and certain times it may be not beneficial. That we have to find it. So all these optimizations we have to do. After that, you can simply dry around say some 100 degrees centigrade or something, because all organic solvents will evaporate in around 40 degrees centigrade. So all these will go away and you will get the aerogel. MOF is a simple solvothermal process is normally used. You have to take a solution which is containing some solvent, maybe in water or DMF, is an organic solvent. You put here inside the salt as well as the organic ligand. and they will combine just like a structure you will get. Now, as I was told earlier, you have to do a solvent exchange, heat in a vacuum, and now you get all the solvents are removed, and you will be getting a network structure like this. And this is called a metal organic frameworks. Both are the preparatory methods, are both are same. This is here we are using a simple solver thermal. There we are using a Solgel. Once aerogel is prepared and MOF is prepared, now you have to mix these two to get an MOFAC. That is the metal organic framework aerogel composites. So far, three methods are available. One is you call the direct mixing. Another is the in situ MOF synthesis, and third one is physical mixing. In the direct mixing method is a simple method. So we have to add, say we can take the liquid precursors, what are needed for preparing the aerogel, you take it, then you add the MOF to this, then you prepare the sol, or you can add the MOF in this stage also. Once sol is prepared, you can add the MOF. In both way you can do. Now you will have a sol MOF suspension. Then you gelate it, by condense it by using the gelation procedures. Then you will get an hydrogel. Then you can dry it. You remove the liquid that is inside, and now you will be getting this MOF aerogel composites. So this is the simple procedure that in any lab you can do it. But the thing is, some important basic considerations you have to see. What is there should not be any concentration gradient while you are adding the MOF to the solvent. What I mean is, suppose if there is a concentration gradient, then immediately the agglomeration takes place. That is, MOF will agglomerate on one side, and your aerogel will be agglomerating on the other side, and you won't be getting a MOFAC. Instead of two materials you will get. So that is one case. How to avoid this? So when we start adding the MOF, you have to constantly stir the liquid for say 6 hours, 7 hours. You have to stir the entire solution. Then you have to allow it for condensation. Otherwise, agglomeration will happen. This is point number one. Second one is the compatibility of the solvent that you are using. Suppose in that solvent, if the MOF dissolves, it's easily soluble in a solvent that you have chosen for the preparation of the aerogel. So aerogel will be obtained, but MOF is easily soluble in that solvent. So then the MOF structure is totally collapsed. It becomes it is dissolved into the solution. So compatibility is very, very important, that MOF should be stable in the solvent what you have taken. And the third one is this electrophilic and nucleophilic concepts. That is, so suppose you are using water. I think it's a nucleophilic. Yes, it's a nucleophilic. And this is an electrophilic. So one will donate an electron, another one is ready to accept the electron. If you are choosing in such a way, if MOF is electrophilic and the water is, say, a solvent is nucleophilic, then MOF and water start to react, and they will exchange the electron and new compound will be formed. So all these three things you have to be careful when we are doing a direct mixing. So this is the important precautions you have. So before starting that one, you have to check whether your MOF is water soluble, whether you are using water in your precursors or your water as a solvent in your aerogel synthesis. All these things you have to check, and you should be very confident that the MOF is not being disturbed while adding to this one. The second one is in situ this MOFAC synthesis. This is also called as a ship in a bottle approach, say where the MOF is called the ship and the aerogel is called the bottle. Here is nothing but you are synthesizing the MOF, you synthesize the aerogel, and in the pore, you add the precursors for the MOF. You can see in this picture, you can understand. So aerogel is here. Now you add the metal precursors to it. Then you add the organics linker to it. Now the reaction is taking place. That is the formation of MOF is happening inside the pores of the aerogel. Now you dry and you can form the composite. Now here also you have to be very careful, because You are doing the process inside the aerogel itself, in the pores of the aerogel itself. Now, what is the problem is, the one thing is the aerogel, sorry, MOF should be strongly bound to the aerogel structure. Otherwise, when you start washing on the final stage, you'll be doing several stages of washing to remove the unwanted, unreacted solvents to be coming out. In such cases, this MOF, if there is a very loose binding, the MOF will go off along with the water. The second thing is, MOF also will have some functional groups, and your gels will also have some functional groups, and these functional groups may make a link, because you are adding an organic linker. Instead of it is linking with the metal ion that is given in the pore, it may link with the aerogel, and some other compound will be formed. So these two things you should be very careful when you are doing an in situ MOF synthesis. And the third one, and this is an image that is in situ MOFAC synthesis. This is a chitin nanofiber in which copper BTC, that is BTC is benzene tricarboxylic acid. So this is a MOF. Copper BTC is an MOF which is being seen inside the fiber. And the third one is the physical mixing method. There are two. The MOF is taken separately, and the aerogels are taken separately. Both are put together, and they are crushed and ground and made into a single material. And this method is very simple. Here, there is no compatibility problem comes in, and the synthetical procedures are very simple. And you need not worry about whether it is a water-soluble MOF or anything. The nucleophilic concept or a electrophilic concept, nothing comes in. You have to prepare both separately, put it into a crusher, you crush it, ground it, and your thing is ready. And this is also advantageous in getting high surface area, because in that cases, as you see later in our experiments, I will explain later, sometimes we will be losing the surface area of aerogel. Will be having a high surface area, and when I add the MOF, it will reduce the surface area in certain cases. But all these drawbacks will be overcome in physical mixing method. And one example is carbon aerogel with copper BTC. You are able to get around 1,236 meters squared, whereas the same thing when we prepared in situ synthesis, we are able to get only 923 meters squared per gram. And the same thing, the volume. There is no mesopore volume reductions is happening in the physical mixing method. So these are the many applications that are being reported, and our work is mainly on solar cells as well as supercapacitors. We have worked on this, and now today I am going to present my final portion of my talk is on nickel BTC MOF titanium aerogel aerocomposite. This is our experiments on photoanode in dye-sensitized solar cells. So the first part, what you call the stabilization, titanium, we want to get titanium isopropoxide. So it is highly unstable. So we have to stabilize this with acetic acid. Then we do an hydrolysis with the deionized water. And you know the ratio is 1:10:350. This is the ratio. We are using the acetic acid, water, and titanium isopropoxide. And then that is the point where we are getting the sol, and that is being condensed by passing ammonia. So we are adjusting the pH of the solution suitable for condensation. We want to convert into a gel, and we are allowing it for aging for about 24 hours at 70 degrees centigrade. Now we are able to get a gel, and this gel is being solvent exchange. As I already told you, we are using N-hexane isopropyl alcohol to reduce the surface tension, because we are using water here. So these two are having surface tension less than water. So we are using the solvent exchange for 6 times, and the solvent is completely exchanged, and then it is dried at room temperature around 30-35 degrees centigrade, and we are getting the aerogel. So preparing this nickel MOF aerogel composite, we will be adding that nickel BTC at this point. So when the solution is ready, now this is called a direct mixing method. This is not either in situ or physical mixing. This is direct mixing method. So we are directly mixing the MOF here. So we have optimized other conditions. And the MOF, what we have considered is water insoluble. That is why we have no problem with the water that is being here. And finally, we are getting a powder like this. So this is the powder-like structure, highly porous in nature. And this is the powder we are getting after drying at room temperature. And if you see the FESM, this is the FESM image. What of the aerogel, what we have obtained is highly porous. You can see it's highly porous, like it's a beautiful flowery structure. And if you see the pore diameter using the bed surface, you can calculate the pore diameter. And if you see the pore diameter, it is ranging between, of course, around 8 nanometer to 30 nanometer. It is spreading. So the pores diameter is spreading from 8 to 30 nanometer. Now to this aerogel, we mixed the MOF, say 0.5% of nickel BTC was added, and you can see the difference. The pores becomes uniformly distributed and is being reduced in size. So this we can check in the bed surface. You can check here. Almost the pores are distributed along 5 nanometers. You can compare this to. Here there is a broad distribution from 5 to 30. Here it is closely distributed around 5 nanometers, and you can see the image. Almost everything is having equal size of pores. Now you can check the surface area as well as bed curve isotherms. You can check. This is for aerogel. This is the bed isotherm, and when we add MOF, you can see there is a difference. So it is nitrogen absorption, desorption studies. So you can see here, it becomes robust. It becomes more strong. This is an indication. This is a type 4 isotherm in the bed surface analysis. And you can see the surface area. For aerogel, it is 252 meters squared per gram. When we add 0.25% of MOF, it is 269, but then it comes reducing. It is reducing below the pure one. And you can see the surface roughness and the pore diameter, mean pore diameter, you can see it is 23.2. As you seen earlier, the mean diameter is very high, whereas it is being reduced. It is around 5 nanometers. One thing you should be very careful, because for solar cell applications, your pore diameter should be around 5 to 20 nanometers. Otherwise, it won't work for this one. Now, why the surface area is decreasing in certain cases and why the surface area is increasing in certain cases, you can see that depends upon how the MOF is absorbed to the surface. If it is absorbing to the surface like this is the pore of the aerogel. Sorry, this is the pore of the aerogel. And if the MOF is sitting on the surface, then automatically your surface area is increasing. So surface area means everything it is includes the pore thing, pore diameter, it goes inside the pores, and if you is calculating like this, you are this one. So the surface area increases. If it goes and fills the pores, then automatically your surface area is decreased. So your surface area will be this one. You cannot go inside the pore. While calculating the pore, you are passing the nitrogen. Nitrogen will not go into these pores. It will be moving along these areas. And that is why the surface area is decreasing. It is not, it is for nickel BTC, it is decreasing. In our experiments, we observed that when we use cobalt, the surface area is increasing. It is going beyond 300. So the reason is very clear. That is nickel BTC, it is having an ionic radius very low, whereas compared to cobalt ionic radius is large. So you cannot go inside the pore, it is sitting on the surface. Now this is the image, and you can see the detailed HRTM image. You can see a very good idea. Now this is the structure what we have proposed, and these are the aerogels, and the blue color or the MOF, because we have added very small quantity. So these are the blue colors we are seeing here. These are the MOF clusters, and you can see that is being reflected on the HRTM image. You can see the dark black portions are the MOFs that what we have added to the structure. And the EDAX also being taken, and the imaging was done on what you call the electron imaging. And you can see titanium is present, oxygen is present, nickel is present, carbon, that is the carboxylic acid, the carbon is also present. And if you see the XPS result, it is very clear. You can see the titanium remains in its oxidation states as well as nickel. And this is the pristine titanium aerogel, and this is the MOF added. And you cannot see anything. This nickel is being, sorry, the titanium aerogel is not disturbed by the addition to certain extent. Now, if you see the XRD and electron diffraction images, you can see the difference. So this is for the pure aerogel that is being indexed here. Now I am adding 0.25% of MOF. There is no major changes happening. But when I go to 0.5%, you can see some additional peaks are coming in. And when I increase to 0.75%, there is a significant change on broadening of the peak takes place. And it is being identified that there is a phase change from anodized phase. This is in the anodized phase of titanium to the rutile. And you know, rutile is the more stable. And so when we start adding the MOF to this, the phase changes from anodized to rutile. And that is being reflected in the electron diffraction images also. You can see this is for pure titanium aerogel, and you can see all the fringes are seen here corresponding to each reflection planes of the X-ray diffraction. You can see the rings are seen here. And if you are increasing that to 0.5%, you can see the difference. And if you still increase to 0.75%, some of the fringes are missing here, and it is showing something different. So what we conclude, the presence, when MOF is added to the aerogels, there is a mixing of phases, the anodized and rutile in the structure. And you can see the crystalline size is around 3.5 to 3 nanometer. And the reduced crystallite size is beneficial for improving the contact between the FTO and the TiO2 substrate. And that is being supporting, because later result shows that the resistance between interfacial resistance is, series resistance is coming down, and therefore there's a fast electron injection. And this is the UV spectra that is being obtained for this. And you can see that for titania, this is the titanium aerogel, this is the curve, and the absorption is being somewhat increasing for the other one. And these are the bandwidth. The bandwidth is getting decreased as we increase the MOF value. Now, how the photoanode is prepared? We take the titanium aerogel, we use isopropyl alcohol, we sonicate. When we spin coat this particular solution, that is what you call a slurry, we spin coat on the surface of the FTO, then we calcinate at a temperature of 120 degrees centigrade for 30 minutes. And we use the standard dye, that is N719. Of course, we worked on porphyrins that Professor Modi will explain in this lecture. And N71 dye we have used here. And the cathode is prepared by using platinic acid by thermal deposition on the FTO substrate. This is the solid electrolyte what we have prepared. I don't want to go into the detail. And the cell area what we used is 0.5 centimeter square. And N71 dye, the formula is here. And this is the formula what is there. These are all standards. There's no problem. And in the polyethylene oxide, there's electrolyte. As I already told you, we have included the iodide salts along with that. So that will be acting as the redox couple for electron transfer. And this polymer is a mixture of polyethylene glycol and polyethylene oxide in the ratio 60:40. And there is electrolyte is a separate area that I don't want to discuss here now because it's very elaborate. And this is the setup what we have in our lab to measure the solar cell parameters. It is called controlled intensity modulated photoelectron spectrometer. So it will having an potentiostats. This is called master one, and this is called a slave one, and this is giving in the iodine adjusting the intensity of the light falling on the surface of the here. Actually, you cannot see the dye solar cells. It is kept here the light intensity is too much, you cannot see it. So the light is falling on the cell, and that is being connected to the master potentiostat, so that everything is software based, computer based, so everything automatically recorded and all calculations will be taken up there. And this is what is being recorded in the SIMS. And this is the impedance spectra, and this is the board plot. And you can see at a close look, you can see this is the close look. You can see the resistance is decreasing. For 0.5 percentage of MOF, the interfacial resistance is decreasing. And you see the board plots, you can have the values here. So for aerogel, it is 19.6 is ohms is the resistance, but when you come for 0.5, it is 17.8. So 0.5% of MOF nickel BTC added to the aerogel is the most favorable condition for solar cells in our findings. And the very important thing we have found out here is the electron lifetime. That is very, very important. You see there is a significant increase in the electron lifetime. Therefore, the diffusion and as well as injection is quite possible. That is reflected. Immediately you can see this is the dye absorption studies. You can see for aerogel, this is the reference, and this for aerogel, that is the lower, this value. For 0.5, it is improving. Of course, 0.75 is improving, but other factors are not supporting for solar cell applications. It may be used for some other applications. And you can see the JV plot here. You can see here, this power conversion efficiency of the solar cell, what we have fabricated is around 8.8. Significant increase in the power conversion efficiency using solid electrolyte, because solid electrolyte is being reported around 10 to 11% by using different methods. In our case, we have reached up to 8.8% in the system. This being reflected on the transient measurements what we have made, and by using the light pulses, we have recorded the time versus photocurrent, how the photocurrent responds to the time. And you can see the photocurrent is very high for 0.5%. It is very high. And you can also see the decay. Of course, I cannot show the enlarged one. You can this one is taking more time to decay. And these are the conditions which favor the increase in the efficiency of the solar cells. And you can see the energy level diagram. This is the titanium dioxide. These are a band gap is around 3.1, around 3.0. This is the dye, and these are the MOFs, and these are the band gaps we have seen in the UV absorption spectra, and you have calculated. So it is easily, the diffusion is easily possible in the, this becomes an intermediate step for the diffusion of electron. So that is the reason why the efficiency is increased. And you can refer to my paper. This is our paper. Of course, Moti is also an author to this. And we have published in Applied Surface Science. It's our, just 5 or 6 months back, it has been published. And you can go through this paper. You can get almost all the details, what I have talked here. You get all the information in details. And also, I'm thankful to Science and Engineering Research Board of Department of Science and Technology, because this project was done by the support of, by their funding of nearly 25 lakhs funding is being supported. So thank you very much, and for giving this opportunity.
Thank you, sir. There is a question which Dr. Lavanya will ask you now. It was asked by a participant.
Yes, sure.
Good morning, sir.
Yes, please, madam.
Mr. Kulasekara Pandit have asked a question. Will the dye-sensitized solar cell contribute towards India's need for 2020?
Yeah, all right. Say energy requirement is necessary for all purposes. It is not dye-sensitized solar cells. Wherever you are able to derive or harvest energy from any source, that is important. It is not one solar energy, it can be wind energy. One thing is it should be a renewable energy source. That is the point we have. Definitely it is going to contribute. There is no doubt about it.
So another question is, those silicon-based solar cells are contributing 100% to society. Why do we concentrate on dye-sensitized solar cells? with poor efficiency?
See, it is always there is a quest for finding new materials for applications. So many things are saturated, but we are always going for alternate solutions. In that way, dye-sensitized solar cells is also there. And one advantage of this one is the indoor applications, which is silicon solar cells cannot be possible with indoor applications. This is possible with indoor applications. So small, low current applications, we can think of this one.
Okay, thank you, sir. And another question posted. Is there any possibility to have efficient construction techniques of solar cell among other southern laboratories?
Madam, please repeat.
Is there any possibility to have efficient construction techniques of solar cell among our southern laboratories?
That everybody has to work to make the efficiency, to make build their own laboratories and find that one. It is possible everywhere. It is not so like that. We are also a college. We are not a university. We have built up our own facilities there. You can visit our website also. That is psnresearch.ac.in, and you can see that the facilities, what facilities we have. And we are also allowing other people to do their characterization, but at present it is not possible. If needed, you can contact us. We will help you.
Thank you, sir.
Thank you very much, sir.
Thank you, madam. Thank you for the opportunity. Thank you.
Sure. Sri Devi, you can go with.
Shall we go to next section, ma'am?
Start. Yeah, you can start.
Yes, ma'am. Thank you, ma'am. Thank you, sir, for the wonderful session. We can go to the next session. I'm happy to introduce Dr. Moti, Associate Professor of Chemistry, Center for Scientific and Applied Research, Pearson College of Engineering. I'm happy to introduce Dr. E.M. Moti, Associate Professor of Chemistry, Center for Scientific and Applied Research, Pearson College of Engineering and Technology. Dr. Moti carried out his PhD work both at School of Chemistry, Bharatdasan University and University de Neuchâtel, Switzerland, and he was awarded his PhD in 2007 in the area of organometallic chemistry. He did research in Switzerland for 2 years. Dr. Moti has been a postdoctoral research associate in Switzerland, IIT Bombay, and his last postdoctoral assignment in the University of Dublin, Trinity College, Ireland, was funded by a highly competitive Irish Research Council grant. He has published more than 25 papers in international journals of high repute and has presented his work in major international conferences in different countries, including the American Chemical Society meetings. He has visited USA, UK, France, Switzerland, and Greece for his scientific activities. He has been a member of professional bodies such as Swiss Chemical Society, Society of Porphyrins and Thalasscience, and American Chemical Society. After his return to India in 2012, he has received Young Scientist Startup Grant from Department of Science and Technology, Science and Engineering Research Board to start his independent research in the area of photoactive molecules and materials for energy and biomedical applications. We are happy to have you, Amit sir. I request you to take over the session. Over to Moti sir. Thank you.
Sure, madam. Thank you very much for your kind introduction. I hope you are able to hear me.
Yes, sir, we can hear you.
Okay. So let me share my screen. Okay. All right. So very good morning to everyone once again. I'm very happy to be part of this e-lecture series, which has brought me here to this platform. Today, we've taken up a very innovative topic, that is solar cells. In particular, that is dealing with dye-sensitized solar cells. Important aspect of this dye-sensitized solar cells are they are slated to be the next generation in the solar cell industry or field, and they have got immense applications, and then a lot of potential, and world over people have started working on it. And of course, it has some limitations. That is where scientists are concentrating their work on. I'm very thankful to Professor Shajan for giving a introduction of this topic. I'm not going to do all these introductions again. So my topic specifically is going to be design of dye for DSSC. Okay, so since I am a chemist, my perspective is towards the chemistry aspects of the dye design. And of course, in order to give a wider perspective, I'm going to talk about IR spectral characterization. So this is not only applicable for DSSC field, but also it is applicable for a wider research community, because it is one of the best or most studied characterization technique. So let me go to my talk. So, DSSC working principle, as Professor Sajan has already given an overview, we have its photo electrochemical cell, which is constructed using two electrodes. One is an anode, another one is the cathode. The anode is made up of TiO2, that is a semiconductor, and then it is loaded with dye. And then on the right hand side, we have a platinized cathode. So in between these two parts, we have an electrolyte. Okay, so that is what I have shown here. So there is on one side FTO, TiO2 layer, and then sensitizer coated over it. And then we have an electrolyte in between the two layers. And then on the right hand side, we have a platinum coated FTO, right? So we are going to focus on the dye, because this is where all the process is initiated. The first step of DSSC starts from the dye. So what happens when we shine light over this system? The dye absorbs the photons, and then it is going to the excited state. That is, the electron is going to the excited state. This excited state, photo-excited electron that is present in the excited state of the dye, can be injected into the TiO2 conduction band. So that is the first step, excitation of the electron from the dye and conduction of, injection of electron to the conduction band. So that constitutes the first step. So then what happens to this injected electron? It passes along the TiO2 and then goes to the electrode and the external circuit, where it is used up as mentioned here as a light bulb. And then the spent electron comes back to this cathode, and then it is taken up by the electrode, and then from the electrode it again comes back to the original dye, which lost the electron before. Now it has got the electron back. All these blue lines represented here are called the forward processes, which are very, very essential, which are required for the performance of that DSSC device. But there are some other unfavorable processes represented here as red lines. As you can see here, once the electron is injected into the conduction band from the photo excited dye, this electron can be transferred across the TiO2 and can go out, or else it can also do two more things. For example, it can go back to the original dye from TiO2. So it can go back to the original dye, and then it can quench the dye, or it can go to this electrolyte. Here the electrolyte is iodide, triiodide. In both ways, what happens is these processes are called recombinations. So the recombination process, it stops the electron from going out to the external circuit. So that means it is detrimental for the solar cell functioning. Right. So as we are concentrating on the dye aspect, so let me tell you some of the important criteria that are required to design a successful dye. So what are the important criteria? So as you can see here in the picture, these white balls are represented as TiO2, which is coated with a dye, which is a purple dot. First of all, why do we need a dye? So why not TiO2? TiO2 itself is a semiconductor. Why not it harvests the solar light? So since the TiO2 is a large band gap material, 3.2 electron volt, it has limitations that it can only absorb UV light. So bulk of the sunlight coming to the earth is visible light, as Professor Arjun has already mentioned, and near IR light. So in order to use the solar spectrum better, we need a dye. So the dye harvests the solar energy in a better way. So what a dye does, basically the dye does is absorption of solar photons. And then once it absorbs the solar photons, it gets excited and injects an electron to the conduction band of the titania. Right. So the first criteria to look for is the optical properties of dyes. What kind of optical properties are required or desired? The sensitizer should cover the wide absorption wavelength in visible and near IR regions. And it also should have a high molar extinction coefficient. That means it should absorb more photons. Right, so here we see a solar spectrum. As you can see here, the sun emits light from 300 nanometer and up to 1300 nanometers. That is from UV light up to IR light. Okay, so here we can see a structure of a dye which is porphyrin based, and the red line represents the absorption spectra of the porphyrin dye. So the absorption spectra clearly shows that it has a strong absorption around 450 nanometers, and then some the absorptions go up to 700 nanometers. Okay, so there is some absorption deficiency here. So what we observe here is that the extinction coefficient of one band is very, very strong. So this dye has the capability to act as a solar cell dye. All right. But as chemists, as scientists are constantly aiming for better things, what we do is we try to acquire more energy from sunlight. A strategy, what we can do here is to extend the absorption wavelength of this dye. So if we are able to extend above 700, 800, 900 like that, more sunlight can be used. And if we can use up more sunlight, the solar cell efficiency will be high. Okay, so with this idea in mind, next we go a little bit in detail into the frontal orbital energy levels. So what are these frontal orbital energy levels? As we would have studied, as most of us know, that any molecule, there are molecular orbitals, and the frontier orbitals, there are two frontier orbitals. They are the highest occupied molecular orbital and the lowest unoccupied molecular orbital. So these two energy levels are very important because the excitations happen in these two energy levels, right? So if we concentrate on this dye part alone, now we can see inside this box, there is an energy level for dye. The bottom line is the HOMO, that is the highest occupied molecular orbital level. And the top part is the LUMO, lowest unoccupied molecular orbital level. So these two parts are there, but how they have to be arranged? There should be some specific way they have to be arranged so that they can participate as a dye in TiO2 DSSC. Okay, so there are many dyes available in nature, in synthetic chemistry. For example, we see all our clothes are colored. So we don't use natural dyes for coloring anymore, but we use a lot of synthetic dyes. So dye chemistry is a great big field where we have hundreds and thousands of dyes being made, but not all dyes can be used for this purpose, for the purpose of dye-sensitized solar cells. So what difference, what specific things we need to have in a dye is that If you can see here, the red box that corresponds to LUMO, this energy level should lie sufficiently higher than the conduction band of TiO2, because only then the electron can be efficiently injected. Otherwise, if it lies above, if the conduction band lies above the LUMO, the energetics will not be favorable. Okay, similarly, we can see the HOMO, that is in the bottom energy level, which is occupied molecular orbital energy level. So this highest occupied molecular orbital energy level should lie sufficiently lower than the redox potential of the electrolyte. Here we have iodide, triiodide electrolyte. So for different electrolytes, the requirement is different. For example, the most used is iodine based electrolyte. And then nowadays we have cobalt based electrolytes, copper based electrolytes. For different electrolytes, the level needs to be in tune with that of the electrolyte. Okay, so this is about the frontier orbital energy levels. So you can clearly see if the LUMO or HOMO is not positioned in favorably to the conduction band or to the redox potential electrolyte, then the cell will not work. Then anchoring group. First of all, the dye molecule should be properly attached to the titanium dioxide material. So if it is not attached properly, then it may not work well, because there is an electrolyte in between the two layers, the cathode and anode, and this may dissolve, or this may leach the dye molecules into the electrolyte. So there should be a physical contact between the dye and the titanium dioxide. So how we can establish this physical contact? We can use some specific organic groups called anchoring groups, rightly said, because they anchor the dye molecule into the titanium dioxide. Only then the electron transfer can happen. So for example, the most commonly used anchoring groups are carboxylic acid groups, COOH, and then cyanoacrylic acid, CN, a group containing a cyano group and a carboxylic group, and then silyl groups. So these are all very commonly used groups which bind very strongly to titanium dioxide. So the strong binding to TiO2 is very essential to ensure efficient electron induction and also device stability, because this device will have to work for several years once it is produced. So if the binding is not strong enough, if the binding is weak or labile, if it is reversible, then the device stability will suffer. Then we have another aspect that is called dye aggregation. Dye molecules, they are organic molecules and they have a tendency to aggregate in solution. And whenever they are adsorbed onto something, they have a tendency to aggregate. But what happens when they aggregate? Okay, for example, here you see the red one is TiO2 and the blue are dye molecules. So the different kinds of aggregations are shown here. The first one, the aggregation is the little bit far away. They are not too closely aggregated. And then the second middle one, they are aggregated very strongly. They are closely interacting. The third one also, some kind of aggregation is there. So what happens when they aggregate? When they aggregate, there is a chance of intermolecular energy transfer. So when the light shines on the photosensitizer or a dye molecule, when it goes to the excited state, it can easily, it's ready to transfer its energy to whatever favorable is present nearby it. If conduction band is present, it can transfer the energy there. If dyes are present, some more dyes are nearby, then it can also transfer the energy to the other dye. Okay, so what happens when intermolecular energy transfer happens? There will be a reduction in electron injection. So the rate of electron injection, the yield of electron injection may suffer because of intermolecular energy transfer. Okay, so that's why we have to design a dye in such a way that aggregation of dye when it is coated onto the TiO2 layer should be minimum. Okay, because or should be avoided completely. So dye aggregation is an important property which reduces the final power output of the dye, DSSC. Okay. Next, the next property is charge recombination. I have already shown two red lines, right? So I'm showing it again. These two red lines are unfavorable or reverse processes which are not desired. Why they are not desired? Because they quench the dye, they quench the electrolyte, and they reduce the final power output. So this charge recombination should be reduced. How we can reduce? We can keep the oxidized dye away from TiO2 surface. For example, if the oxidized dye, when light is shined upon it, it becomes oxidized or excited. So once it is close to TiO2, what happens? It can give, the TiO2 can give the electron back to oxidized dye. Okay, so we should in a way do a process by which the oxidized dye is not very close to the TiO2. So this is done by increasing the distance between the anchoring group and the dye. For example, if you can have a spacer, so that can give the enough required space between the dye and the TiO2, so that only the photoexcited electrons injection happens and not the reverse recombination happens. Similarly, there should not be the electrolyte. Okay, so the electrolyte also should not be very close to the TiO2 surface. If the electrolyte is touching the TiO2 surface, then this recombination can happen very easily. So what we can do, the solution, there should be a layer or a coating in between the TiO2 and the electrolyte to avoid this recombination. Okay, so all these things can be done by designing dye itself. For example, the dye molecule can have a long alkyl chains or long chains which repel the electrolyte, which does not allow the electrolyte to come near TiO2. Okay, then the chemical stability and then thermal stability. Since the dye molecule is always in contact with this electrolyte and also with TiO2, chemical reactions may happen, and these chemical reactions must be avoided to save the cell for long-term usage. And thermal stability. This DSSC that is made using this dye will be exposed to sunlight. It will be exposed to the harsh lighting conditions and then the heat that is generated from the sunlight. So high temperature may be there, it is exposed to temperature, and then constant heat, bombardment of photons. So these things should not affect the dye. As you everyone must have seen that most of our clothes are dyed using organic dyes. So if we leave these clothes in open sunlight for a long time, what happens, we would have seen a fading of the color. So what happened during this process is the dye molecule is deteriorated or destroyed by the sunlight. Okay, the free radicals that are produced destroy the dye molecule. So this happens in the DSSC dye as well, but it should be designed in such a way that this should be avoided or minimized. Okay. So this helps in long-term stability, and then it should be protected from oxidizing agents such as water and oxygen molecules. As I already told, long alkyl chains and structural modifications are useful for doing this job. Right. Now, this brings us to an important point where we can tailor the properties of dye. How we can tailor the properties of dye. So dye molecule is basically an organic molecule. We can attach different groups. So there is always a possibility to attach different groups. So here I have shown the sensitizer. We can see in the bottom the conjugation length. So if we can increase the conjugation length, the double bonds, the triple bonds that are present in the dye molecule, then we can change the band gap of this dye. And also, if we can change the peripheral groups, for example, electron donor groups, electron acceptor groups, then also we can change the band gap. So what happens when we change the band gap? So when we reduce the band gap, this will make the dye to absorb more light in the visible region. If we reduce it further, then more light from near IR region will be absorbed. Okay, so these kind of dyes are nowadays very popular among scientists worldwide, especially professors from Japan. Universities in Japan are working how to reduce the band gap of the dye molecules. What are the different ways we can do so that the dye molecule band gap is reduced and it starts to absorb or harvest more sunlight from the sun spectrum, right? So what strategies we can use? We can use a strategy very common for chemists, that is attaching different substituents. But the substituents must be chosen in such a way that a donor group is there and an acceptor group is there. Okay, so the donor group can be changed and acceptor group can be changed. Why we need to change all these things? Because we will never know which dye will work better for a particular DSSE. So we need to constantly tune the dye, right? Then we can increase the pi system. We can introduce between the donor and acceptor a pi system. Pi system is the conjugation. So in this way, what happens? We can reduce the band gap. And also now we have got a flexibility that we can change three things. We can change the dye, we can change the pi system, and we can change the acceptor. If we can modify a single component and see what is the effect of each component for the DSSC device, we can finalize or we can choose the best performing dye. And also we can use additional donors and additional acceptors that is shown in the bottom. So what kind of donors we can use? We can, architectures we can use. We can, for example, add two donor groups instead of one donor group here. And then we can add another acceptor group. I mean, two acceptor groups we can add. So it's all, there is no rule for it. Only thing is we need to have the creativity. So we need to apply our creativity and then we need to devise the architecture of the dyes and find out the best performing dyes. Okay, so that is what happening worldwide. So these are the different ways we can tailor the properties of dyes for specific DSSC applications in order to improve the power conversion efficiency. So let me show you a simple organic dye here. As you can see here, the D represents donor group and A represents acceptor group. Okay, so the donor group is nothing but a triphenylamine, which is electron rich group or molecule. And then the acceptor group here is a cyanoacrylic acid. It has a carboxylic acid group and a cyano group. So it acts as an acceptor as well as it can act as a anchoring group. Okay, so it functions in both ways. So and in between we have a phenyl ring and then a carbon-carbon double bonds, and all these things are pi systems, or they can increase the conjugation, thereby they can decrease the band gap. Right, so with this basic idea in mind, I'm going to show you some dyes which are which may look a bit complicated, but they all follow a simple logic what we have shown before. Okay, so there are three different kinds of dyes available and widely researched worldwide. The first thing is ruthenium dyes. The ruthenium, as you may know, that is very expensive element. It is more expensive than gold. And this ruthenium metal, when it is coordinated with the polypyridine groups, okay, polypyridine ligands, it has the photophysical properties very much suitable for our dye-sensitized solar cells. So what they have done here, if you can see the one structure on the left-hand side, top left-hand side, there is a bipyridyl group. Over the bipyridyl group, you have a carboxylic acid, and there is another carboxylic acid. So what this carboxylic acid is used for? It is used for anchoring to TiO2. And on the left-hand side, you have another bipyridine ligand, which has a long alkyl chain. As I told you before, in order to reduce the recombination, we need to have long alkyl chains. And then we have a carbon bridge. Okay. So this is the architecture of ruthenium based dyes. You can see different variations here. On the right hand side, you can see a long chain, but this is not alkyl, this is alkoxy. You have oxygen in between. Okay, so that is the only difference. And the carboxylic acid is same, which is present as a salt in this here place. And then the third structure, you can see a pi bridge introduced between this bipyridine ligand and the long alkyl chain. Okay, and then this fourth structure, you can see instead of a carbon-carbon double bond or triple bond, we have a heterocyclic group, which is thiophene group, which again acts as a pi bridge to enhance the light absorption characteristics. Okay, so these are all the different ways we can modify the ligands over the ruthenium center, so that ruthenium dyes can be made in different ways. And they have for about up to 2008 or 9, they were the best performing dyes in the DSSC field. And then another type of dyes called zinc porphyrin dyes. So these porphyrin dyes are what we are working with. Porphyrins are nothing but molecules having this kind of a structure. You can see four pyrrole rings. Okay, it's the tetrapyrrole. So this ring is very, very common in nature. We have this in our blood, that is hemoglobin. The heme, the molecule of heme has this structure, but we have an iron metal in the middle. And then in plant world, the green color for the plants is due to a similar kind of a ring having a magnesium atom in the middle. Okay, that is chlorophyll. So both plant and animals, they have colored molecules that are based on porphyrins. So it is chosen by nature for a variety of reasons. They are very, very stable. They're very stable to light, very stable to temperature, and very stable chemically. But they are also, we can also do a lot of modifications. So they are not inert for chemistry, but they are stable enough for doing different structural modifications. So we are working on this field. I'm not showing my research here because this is seminar Department of Physics, and I know that many of you will be physics students or professors, so I'm not going into very much details. But what I want you to look at is that this porphyrin ring, what kind of groups they have attached over it, the peripheral groups. Here you can see C12H25. So this is a long chain. So 3 long chains on both sides, and then you have an anchoring group, COOH. And then in between this porphyrin and anchoring group, you have a triple bond, that is pi extension, right? Similarly, the another dye, it's very, very similar. And only thing is the carbon chain position is different. So it is in the ortho position. In this position, the advantage is it can go around the porphyrin. So it can shield the porphyrin ring from the electrolyte. Okay, so it is specifically designed for that purpose. And here the third dye, it's a little bit different. You have a tertiary butyl group on both sides, and then you have pi bridge on both sides, and one side you have an anchoring group. Okay, on one side you have a donor group, dimethyl amino group. And then the last dye is very, very similar. Only thing is you have this long alkyl chain on the ortho positions. Okay, so that it can encircle the porphyrin ring and protect it from the electrolyte. Okay, so these are all the concepts we look at when designing a porphyrin dyes. And then since the ruthenium dye is very, very expensive and the porphyrin dyes are a little bit difficult to synthesize in the laboratory, people are now looking at metal-free dyes. So what kind of dyes that can be made in a simple way that does not use any metal or expensive metal? So these are some of the dyes which are metal-free. As you can see here, this is very similar to what I have shown before as a molecular model. This is a triphenylamine group, which is a donor group. And then we have an acceptor group here, okay, cyanoacrylic acid, and then a pi bridge here, okay. So what happens here, this is anchored to the TiO2 and then electron transfer happens. So slight variations are given. Instead of a double bond, there is a single bond here. And instead of these groups, there is a diethioneal group here. And then there are two diethioneal groups. And then there is another intermediate group. Okay. So these are all the variations which chemists work on so that we can strike the gold. For example, we can strike the best sensitizer. Okay, so this brings us to the summary of what I have shown you before. So my talk, as I told initially, it consists of two parts. The first part, to summarize, when choosing a dye for DSSC, we have to keep, what are the things we have to keep in mind? The light absorption characteristics, tunability of the HOMO-LUMO band gap, and then anchoring group, how much or what kind of anchoring group we want to have, dye aggregation phenomena. We need to have a molecular structure which does not allow the dyes to aggregate. And then the cost of the dye, that is the most important part here, because the dyes cost really huge in dollars. Okay, so $2,000 per gram, like that. So how the cost goes up? By using expensive metal like ruthenium. So if we remove that metal ruthenium, we can reduce the cost. So these are the points we need to keep it in mind when choosing a dye for DSSC. All right. Okay. So now a little bit to shift your attention to another completely different topic. But why I chose this topic is because we want to give an overview of what kind of characterizations we do for DSSC field. And not only for DSSC field, there may be people who are working in different kinds of molecules. They may be doing crystal growth, or they may be having different projects. They may be using molecules or materials. An infrared spectroscopy is very simple tool to find out what material they have and what kind of changes that has taken place. Okay, so I will be giving a very brief overview. So I'm not going to go into many details. I will be focusing on organic compounds, and I will want to know you just by looking at the IR spectra, how you can find out what molecule is there. Okay, so as you know, IR spectra is always a complicated pattern of peaks, and by looking at it, people get confused. They don't know where to look exactly to find out the desired peak. Okay, so as I told you before, for molecular identification, we use the entire electromagnetic spectrum, and each wave is used for particular excitation. For example, UV we use for electronic excitation, and IR molecular vibration, and NMR uses radio waves, and X-rays we use. So we are going to focus on IR spectroscopy now. So just give you maybe a 10-15 minutes of brief overview of IR spectroscopy so that you can learn from there, and then you can go on to master the skills. Right. IR spectroscopy, it uses molecular vibrations. Okay, so it detects the molecular vibrations. Covalent bonds generally can be visualized as having attached between a spring. Okay, it having a spring in between it. So in this way, it oscillates. When this oscillates, when the atoms are different, there is a change in dipole moment. When a change in dipole moment happens, there is an electromagnetic field that is produced. When this electromagnetic field, this electromagnetic field is usually in the IR region, and then when we pass an IR beam to this molecule, this electromagnetic radiation can couple. So if the specific radiation happens to come near, it can couple with that radiation, with that wavelength, and then a coupled wave is produced. That means an IR radiation has been absorbed by the system. So this is what we see as an IR spectrum. Okay, so IR spectrum, we see when IR radiation is absorbed by the system. Okay, when the system does not absorb IR radiation, we don't see any spectrum. Okay, when does the system absorb IR radiation? Only when there is a change in dipole happening due to vibrations. Okay, so different kind of vibrations are there. So let me just tell you two kinds of vibrations. One is stretching, another is bending. Okay, stretching you can see here, symmetric stretching, and then asymmetric stretching, and then bending vibrations, in plane bending, and then out of plane bendings, rocking, and then twisting, wagging. All kinds of vibrations are happening all the time in the molecule. Okay, so in order to understand the concept, how to identify or how to interpret the IR spectra, I'll just introduce to a concept, a very simple concept. I'm not going to very details. So we can visualize a CH bond as, for example, here we have a CH. A carbon is connected to another hydrogen through a spring. Okay, bonds as springs. Just imagine, as you can see in the picture, on one side of a wall, a spring is attached, and then there is a box attached to the other end of the spring. So when you pull the spring, and just imagine, consider that there is no friction here. When you can pull the box and leave it, it can oscillate, right? It can displace, go back and forth, it can oscillate. So this is a familiar concept or topic for physicists. It's a Hooke's law. And this is Fs is force on spring, and this is given by minus kx. Minus comes because this comes back. Okay, it's a recombinant force. And then the k is a spring constant. Okay, when the spring is strong, the k value will be high. When the spring is weak, the k value will be low. For example, if the bond between the carbon and hydrogen is, or bond between two atoms is strong, the k will be strong. If it is weak, it will be weak. We can relate this to frequency as well. So I'll just give you the final equation here. So frequency is related to k, which is directly proportional. And there is another m, which is mass of the system. Okay, when the spring constant increases, the frequency increases. That means when the spring becomes strong, you get high frequency. When the mass becomes higher, you get lower frequency. Okay, so with this in mind, we always have two atoms at least connected to the spring. Okay, so instead of m, we use a reduced mass here to account for two atoms. And for specific carbon hydrogen, the reduced mass, when we calculate, we can calculate using atomic number of carbon and atomic number of hydrogen. It comes at 0.923. And for carbon-carbon single bond, it comes 6. And carbon-carbon double bond, also 6. But what happens here, the reduced mass is increased from CH to CC, and the frequency will be lowered. And for the carbon-carbon double bond, reduced mass remains the same, but the spring constant is increased. That is, the strength of these two bonds is increased. So K increases and frequency increases. Okay, right. So this is what you have to keep it in mind. Two aspects. One is the force on the spring, that is how strong a bond is. And another thing is how, what kind of atoms are attached to the bond, how heavy the atoms are. Okay, how strong the bond and how heavy the atoms are. These are only two things we need for interpreting the IR spectra. So this is the common IR spectra we see. So it is given in percentage transmittance. The transmittance is 100%. That means no IR radiation has been absorbed. And if it is low, that means IR radiation has been absorbed. Okay, usually IR spectrum x-axis is given wave numbers, okay, in the units of centimeter inverse. So we use wave numbers because it equates to higher energy, high frequency and high energy. Okay, and also it gives a very real numbers rather than frequency units. IR spectra is generally absorbed between 600 to 4000 centimeter inverse. So this is a typical IR spectra, what you see. when you record for any of your compounds. So it has, as I told you before, two things. Lighter atoms will have higher energy, okay, or higher frequency. Stronger bonds again will have higher energy or higher energy oscillations, okay. So we don't need all these things. There are different kinds of bonds: strong, medium, and weak bonds, and broad bands. In general, IR is used to detect functional groups, okay. So this is the most important part. This IR spectrum, we see different colors. The orange color is called a fingerprint region, where you get very little information about the molecule or the compound. But the other part, the yellow, green, and blue, they give you important information about the functional group that is present. So they are called a functional group region. This region is called fingerprint region. Okay, this is also called a diagnostic region. Okay, so when you see a IR spectrum, don't worry about fingerprint region. Try to look at the diagnostic functional group region. Okay, so if we have a simple organic compound like an alkane, okay, only carbon and hydrogen, what kind of IR spectra we will have? We will have two prominent bands. The major band, the strongest band, is due to carbon hydrogen. As we know before, hydrogen is a weak, a small atom, a very less heavy atom. So it gives a strong energy vibrations. So it happens at higher wave numbers, okay, than the carbon-carbon bonds. And then what happens when you have a carbon-carbon double bond? This double bond can be clearly seen as a weak band in this region around 1600. And then this carbon-carbon carbon hydrogen single bond is also very clearly seen as in the higher energy regions or higher vibrations, higher wave numbers. Okay, then carbon carbon triple bond can see a very specific peak. Don't here you see a lot of peaks in the fingerprint region, but don't worry about fingerprint region. Just focus on where the carbon carbon triple bond comes. It usually comes at around higher wave number regions as a specific sharp peak. And then you have carbon hydrogen. Because it is a terminal carbon hydrogen bond, it's also seen as a sharp peak. Then when you have a aromatic compound like a benzene ring, okay, so where this, how we can identify them? We can specifically identify them using a set of bands appearing around 1800, 2000 to 1800 region called overtones. And then you have carbon hydrogen bands, but this is very diagnostic in nature than the other things. As you can see, what about the substituents? If you have a mono substituted, di substituted, what about different regions of substitution, ortho, para, meta? All these can be seen in different ways in this overtones. So you have very slight changes, but they are clearly visible. And then you have different unsaturated systems. I'm not going to details. And then when you have other than carbon, a heavy atom like oxygen, when you have a heavy atom, it can be clearly seen as a big broad band. Okay, here you see this carbon oxygen bond around 1050 to 1150 region. When you have an alcohol, that also comes as a specific band, but not as broad or strong as that of the ether one before I showed before. Okay, so here you have OH bond broad. This is because of the hydrogen bonding, which I will be telling you later. All right, then what happens when you have a nitrogen group? So nitrogen and hydrogen attached to carbon, again there is a specific band around 3200 region, okay, for this NH stretch. And for carbon hydrogen, it is around 1590. So this is a primary amine. So it has two hydrogens attached to it. There is a secondary hydrogen. This is only one hydrogen attached to it, two carbons attached to it. What happens here? You can see there is a change in the NH band shape. Okay, previously it was a shape of a W, and now it is shape of V. right? So there is a difference between primary and secondary amines. So this is what, if you can pause and review for some time, this is what we have to see. So we have to, when it comes to hydrogen, we have to look for the shapes. Okay, so if it is broad, it can be OH. If it is sharp, it can be C triple bond CH. If it has a V shape, can be a primary, secondary. W shape can be primary. Small peaks, it can be like phenyl or any other double bonded attached. So we have to learn shapes, not wave numbers, above 3000 centimeter inwards. Okay. So when you see there is a carbonyl group, C double bond O. This is one of the most famous groups to see in IR spectra. When carbonyl group is present, anybody can tell by looking at the IR spectra that there is a carbonyl group. Okay, 1720 to 1740. So all these carbonyl groups, C double bond O, can be seen as the most strong peak. Okay, or the strongest peak. So here again, you have a carbonyl group and also an ether group. Both are very clearly seen, but carbonyl is strongest. Here, carboxylic acid, which has a carbonyl and a OH, COOH. The carbonyl is very clearly seen, and the OH can be seen as a very broad peak. Here you have a propionic acid anhydride, a C double bond O and C single bond O. Both are very clearly seen. Since there are two, they are little bit split. Okay, what happens when you have a chlorine? Chlorine is a heavy atom. When you have a heavy atom, it can also give rise to a specific peak. In this case, around 1770 to 1820. So because it is very big in size, when the mass is very high, the frequency will get reduced. So this we can see around this lower frequency region, around 900 or something. But when we have higher halogens, iodine or bromine, we don't even see it here. Okay, this goes out of the spectra. Then a carbonyl in presence of amine, how it looks like. A carbonyl is clearly seen around 1700, and then the NH2 is also clearly seen. And then nitro group. Nitro group has nitrogen oxygen bonds, both single bond and double bonds. They are seen as two specific line shapes. And then what happens when we have a carbon triple bond nitrogen? This is also very clearly seen. As you can remember, carbon-carbon triple bond was little bit shorter than this. Now carbon nitrogen triple bond is very strong band, but very sharp peak. Okay, this is because of the atomic weight of the nitrogen. Okay, so conjugation affects the IR spectra very much. I'm not going to detail. And then the steric effects. What happens when there are different groups which are near to the carbonyl group. So this carbonyl group, 1686. When there is a methyl group, 1693. So there is a definite change. What happens when there is a steric strain? The molecule is very strained. Then also the carbonyl group frequency varies to a large extent. Okay, and then the final part of this talk is the IR bands of hydrogen bonding. So hydrogen bonding we can very clearly see from IR spectra. Okay, all right. What happens when we have no carbon, hydrogen, oxygen, only inorganic material? For example, TiO2. So covalent bonds, they have vibrations and they can have absorption in the IR region. So no matter they have carbon or not, any covalent bonded molecule can have an IR band. Only thing criteria is that the vibration should have change in dipole moment. Only then the IR radiation will be absorbed. So different systems, for example, water, ammonia, SnCl4, all are having a good IR spectra, inorganic ions, nitrate, carbonate, sulfate, acetate, everything has good IR spectra. All are inorganic. Okay, so last topic to look at is the water. What happens when we have water? Water is shown as a specific peak above 3300 or so in the IR spectra. The liquid water can have 3 bands and the most commonly observed band is above 3000, okay, as a very broad band. Sometimes water can be in the lattice, sometimes it can be coordinated, sometimes it can be just be absorbed. All can be seen in IR spectra very clearly, and unfortunately we cannot distinguish between them. So when we have this adsorbed water, they affect your IR spectra very much. That's why when we measure an IR spectra, we have to be very careful to exclude water or moisture in the system. That's why we use all the things in the desiccator, and mostly what we do is we use a hot air oven, and then we take our KBR directly from the oven and use it. Okay, so we don't keep it in the room temperature or ambient atmospheric conditions because of the problem water absorption can make to this system. Okay, so this brings us to the end of the lecture, that what we have studied so far is we have studied about the IR spectrum and how to interpret the IR spectrum in a simple way. So IR spectrum is a complicated thing. Just by looking at it, nobody can tell what kind of molecule is there, but if we can go into specifics, okay, for example, if we go into the diagnostic region, then we can see the changes happening. Okay, and some caution has to be observed when using when to exclude the moisture in the system. Otherwise, what you will see is a very broad peak that nobody can understand the IR spectra at all, right? So thank you very much. So this is the end of my talk, and I just like to acknowledge that for many figures and references I have taken from internet sources, and these are the books I have referred for making this talk. I hope this will be useful for you for your research. Thank you very much. I welcome any questions.
Thank you, sir. There is one question which Dr. Lavanya will ask you now.
Sure. It is not audible.
Sir, Mr. Karthik Raja has asked a question about to explain about the porosity and electronic structure of dye molecules.
Okay. Dye molecules, as the name says, they are molecules. All right. So they are not materials. So porosity is a concept where usually we see in materials because they are aggregated and then there are pores in between. But these are all molecules, and as such, they don't have any porosity when they are dissolved in a liquid. Maybe in their solid state, they could, but usually they are tightly packed. So we don't see any porosity in between them. We can see the crystal structure of certain dye molecules. They are very tightly packed molecules. So as such, there is no porosity for dye molecules. Okay, in normal circumstances.
Thank you, sir.
Thank you.
I think it's time to wind up. So it's my pleasant duty to deliver the vote of thanks now. First of all, I thank Lord Almighty for making this occasion to occur. And on behalf of the Department of Physics, Anne Hazra Women's College, express my sincere thanks to our college management and EduSex Forum for giving us an opportunity to conduct this lecture. I sincerely thank our principal ma'am, Dr. K. Rajab Fatima, for the constant support and guidance to organize this event. Thank you, ma'am. And I express my sincere gratitude to the speakers, Dr. X. Suresh Arjun sir and Dr. E.M. Murthy sir, for sparing their valuable time to be with us today and delivering such a wonderful lecture. Both the lectures were very informative and useful, sir. Thank you, sir. Next, I would like to thank our head of the department, Mrs. Aisha Nilofar, and my colleagues for their kind support and encouragement. And I sincerely thank all the other teaching and non-teaching staff of Rania Hazra Women's College who rendered their helping hands in the background to organize this event. and express making special thanks to all the participants of this e-lecture for making this program a successful one. Once again, I thank you all from the bottom of my heart. Thank you.
Sir, there is one question. Can you explain about nanoplant like morphology? Can you explain? Can you explain about nanoplant like morphology?
Okay, the question is not very clear, but what I understand, what I could derive from that is they're talking about the morphology of the dye. Is that right? Probably yes. Okay, so dyes, as I told, they are organic molecules. They have different morphology depending upon the packing arrangement they have in the solid state. Usually we don't, since they are organic molecules and they are having different phenyl groups and they pack very tightly, and we don't see any porosity, as I told already, and these molecules have different crystal structures also, and depending upon the packing arrangement they can have different morphology. Okay, so it's not very easy to tell what kind of morphology a particular dye will be having. Depending upon the crystallization conditions and the packing arrangement they have different morphologies.
Okay, sir. Thank you very much.
Thank you very much.
Thank you. Thank you. Yes, Buma?
Yes, ma'am.
Yeah, we can leave the meeting.
Okay, thank you.
Thank you. Thank you, everybody.